part of this system when you hook it together is also kind of challenging. But what I'd like to do is run through what the next section's going to be, so that those who are ready can keep going ahead if they would like to go ahead. And then what I'll do is I'll just come back for those who are stuck on things and come around and help you out. So.
Xilinx, where are you? Oh, and then quick Verilog question or Xilinx question for Dr. Schubert.
Sure.
One of the big issues I was having, like, came when I was trying to simulate. It wasn't recognizing my text fixture as a test fixture. Like every time I hit simulate, it's like, what do you want me to simulate? Like you don't have any like simulation type of stuff.
Oh, when you right-click and go simulate, you really got to make sure in your left menu that you have the right thing selected.
I did.
Because it's
You
done that
have
to
to
me
check
several
that, and
times.
then the radio buttons, right? You got to make sure those are set. There's a simulate versus implement radio buttons, and then pick the right one, and then it usually does. The other important thing is when you load it in the first time, you either have to just load it as a file and make sure there's no parentheses so it knows it's top level, which means it's a test fixture. If there's no inputs or output ports, then it must be a test fixture. Or if you're going to start from ground zero, you have to tell it it's a test fixture.
Right. So like this right here. I mean, I don't know if you want to take time to look at it. Like this is
real
fine.
quick.
This is the test, right? That you wrote. When I go to simulate this, that's what it shows me. And the problem that's happening is because it doesn't realize that this is a test bench. So every time I do it, I have to reload it in from scratch.
Huh, that's an odd.
That's an odd error, right? I know.
Yeah.
And it's only specific to this computer. It was happening on a few other computers whenever I tried my stuff.
I mean, that sounds like it's actually a problem with its own internal caching system, that it's corrupting the state. Oh yay, a Firefox update. Ask later. Okay. So we want to talk a little bit about the register file itself. Usually the first thing you want to do is, just like when you're programming, you want to understand the interface, and then you want to understand the inner workings, and then you can code. So it's a good general practice to go. Look at the interface, understand the basic operation inside, then you can code the implementation. So let's walk through this on this. Right? The registers, in order to access a register, you need a clock pulse. You need to know how to time this thing off. It needs to know when a command is issued. Why?
Well, it doesn't need to do anything unless something's being issued.
Once something's been issued, you are accessing two data elements and telling it what you're writing to. Every time a command is issued, it has to do work. The same way that the adders with the reservation stations had to do work. So too, this has to do work. But instead of getting values, it's given addresses. It needs to know which registers. So it needs to know the A address and the B address and the destination. This is source 1 and source 2. Right? And then the destination, who is it being written to. Notice these are all 5-bit numbers. Why is it 5-bit numbers?
Because we're writing 2 of the 5.
2 to the 5th or 32
bit
registers.
Right.
I have 32 registers. It takes 5 bits to address 32 things. Right. So that's this, right? And that's your standard stuff you could pull directly out when you parse it, like 401, when we pull and you pull up the source 1, source 2, and destination as it goes on. This is just being passed in. The in data, in source, right? What are those?
Data is a 32-bit word. That's your data.
Data for what?
From your adders.
To write to the registers.
Right.
Okay? Where's it coming from?
Your adders.
Your ALU.
Or your
The
AL.
common data bus.
Right.
Okay? The adders write to the common data bus, but other things could write to the common data bus. Right? The common data bus is where all the answers come in. So this is actually in data and in source are 2 of the fields from the common data bus. Right? This is the data line, and that's who's sending. Well, it's going to be used exactly the same way for an update. We got to say, who is it, who's talking, because the individual registers inside here can rename things. They need to know, hey, am I getting my final value? When the destination comes in, it says, oh, somebody new is producing me. I have to gotta wait for their answer. This is where that answer comes back. So there's going to have to be an update stage. It's going to have to be an issue stage to handle this, and an update stage to handle that. Right? What about write? I'll get back to this in a second.
That's your right flag.
Why do I need it?
You need to know when you can write something to your registers.
I need to know when to listen to this. Remember, this is part of the data bus. Write tells you when the data bus values are good. There's always something on the data bus.
Oh, okay.
Right? It's not guaranteed to be a legitimate value, right? Somebody writes something in the data bus, when they stop writing, it's going to float to whatever. It'll be something. Right? It just won't be legitimate. So only when write is asserted will you listen to what's here. They have to have some flag for it. So these three make up the part of the data bus that we want to listen to. Okay? So what's this whole deal with RS calculating value?
This lets you know which reservation station is currently doing the ALU operation.
Like, which one is going to be producing your result?
Right.
Remember, destination tells me which register is going to be produced. Who's producing it? This reservation station. Remember when you had the update on the other side, right? Before update, we said what was the available reservation station? And we said we were going to always schedule into that available reservation station. I said that was really important because I can't tell this one after the fact where it was sent to, except to check things. This one right here, when I say I'm going to this particular register, it has to know before it is sent the data out who's going to be producing its result. That's why you have to make an answer available to it beforehand. So this one says if we say, hey look, I'm the adders, and this is the adder that will produce the next answer, when somebody comes and says this register needs an answer, it knows it's coming from that reservation station. Because it knows that's who it's going to get assigned to. That's just the way the rules work. Whoever is the highest priority station is going to do the work.
So DEST is the one requesting the answer.
Destination is which register. Notice it's 5 bits. Right? RS calculating value is the reservation station that will calculate the answer that will go into that register. This is 6 bits. Remember we said there were 6 bits worth of these reservation stations? So we had 64 potential reservation stations. We have 32 registers. This tells me which register needs its value calculated. This one says this is the reservation station to do the work. So this register will wait for this reservation station to produce its result. Does that make sense? So this is why it was so crucial that you said not only that I'm available, but who's available. Because the who's available is what's going to connect over to here. The reason why I'm covering what these are in the other areas is because now you have to make an instantiation of your adders, and you have to make an instantiation of your registers. You're going to have to connect wires. So you have to connect common data bus things here. Right? This is going to have to come from outside the system, some of the issuing commands. That's going to be the test fixture. The clock and the issue command, that's all text fixtures. Text fixture stuff. So all these up here are from the text fixture. Right? But the data and source and write are going to be coming from the common data bus. RS calculating is coming from which is the available reservation station from your adders. Okay? These are now your outputs. A out and B out is one of the values of A and B. And remember what the format had to be? If my value is good, you pass the value.
Right.
If it's not good, if somebody is producing it, so the data I have inside my register is no good, then what am I supposed to do?
Wait until it's good.
I have to pass the address of the reservation station that is producing it. So this is the one that will now produce it, and then you have to set the flag.
So how do you know?
Because we're going to actually have data. I'll talk about the internals.
Gotcha.
But before you had just registers,
Uh-huh.
now you're going to have registers and tags.
Mm.
And that tag is going to, you'll have one extra column in there that's going to tell you who's producing me. And if producing me is 0, it means the data value is good. If producing is anything other than 0, it means that's the reservation station number, the one who's making it. But we'll go through that in detail on the inside.
So from the adder, when you got like an A invalid or B invalid, you'd set your QJ or QK to the address that's coming in on A or B. Did you need to specify that it was like 5 through 0 or 4 through 0, whatever it was, that it was the last bits of A?
No,
Or will it just grab those automatically?
it automatically grabs from the right
All right.
and truncates.
So if you were building this, I mean, you can't really on FPGA, but it would throw a bunch of warnings for all those
Yes,
wires that got
so you are correct on that, right? I don't have to. Verilog will technically do the correct thing. But just because Verilog does the correct thing doesn't mean that it's good coding practice. Okay? It is much better to actually stipulate exactly which bits you're going to be using as it goes. And the reason why that's a much better practice as it goes is because then somebody later on comes down, how do they know whether you screwed something up or you meant to do that? Okay? If you actually deliberately code it so that they see, oh, they really do mean the right 6 bits, then they go, okay, we're fine, that makes sense. And away they go. If you don't do that, then they go, oh, I have no idea what he's talking about. Maybe he messed something up. So you'll throw your human beings quite high here if you don't do that. But technically, Verilog will be okay with it. So, does my interface make sense?
Yes.
So, I mean, technically, at this moment, you ought to be able to write the interface portion of your lab report.
Yeah.
Because that's just what we did. We just walked through and I gave you a brief statement of what all of those are. The reason why I suggest you think about this, if you wait to the end, then it's going to become very painful to try to remember everything that was said. If you write them quicker, it'll take you less time. When you have to come back to refer to it, you'll also be able to find it quicker. So I heartily encourage you to consider that. All right, let's see. Where's center of mass of the class? Looks like it's more to this side. Sorry. All right.
Dave, you stole my spot anyway.
I know, that jerk.
You need me to turn my back and you guys can settle this?
Now we have an IEEE meeting on Thursday.
Okay. Okay, so let's think about what we've got to do inside. We're going to have 32 registers. Your standard system, when you go on, will declare the regs. And how do I declare 32 32-bit registers?
What, the syntax?
31 to 0, X, brackets, 31 to 0.
Your bracket before will give you the width, and the bracket after will give you the width.
Oh.
Right? And then I need, you can do 0 to 31. Now you can't call it reg, you might want to call it reg file or something like that. Can't do reg, just keyword. So I think I called mine reg underscore file. So this one is actually declaring that, let me think, the 31 to 0, the first one is what?
Is your width.
At how many bits in here? It's telling me it's a 32-bit numbers that I'm storing. The second one tells me the number of the spaces. How you order them as they're in there.
So each field is 32 bits wide, right?
Each one is 32 bits. So I just told you, give me 32 32-bit numbers. Right? Just think of this as a 32-bit number, and I want 32 of them. Makes it easier to remember. Okay. I have a second thing that I have declared here, which I call redirection or something. Yeah, redirection. So in addition to this, this would just be your normal kind of reg file as it goes on, where I have 32 storage locations. But we're going to append onto this tag bits, just like in cache.
Right. So that's if we're waiting for a result, right?
All right, so this is the actual registers. This is the redirection. And I call it redirection because it's called a redirection buffer. But it's like tag bits in a cache. Right? It's extra information that's on there that gives you something about the data. It tells you some information that's been tagged up. In our particular case, the only thing we need to know is who's producing it. If the one who is producing it is 0, 0 by definition is the register file. That means the register file is good. If it's anything other than 0, it means the register file is bad, and whoever has that reservation station number must be producing it. So the reg file you can think of as reservation station 0. Okay? So, i.e. data's good. So if this field holds a 0, the data's good, send it out. If this field is non-zero, the data is bad, send the redirection value out. That is the one who will produce it. In addition to that, if somebody says that there is a particular source that's producing an answer, and there's a non-zero value in here, say 5 or something, it means I'm waiting for reservation 5 to produce my answer. If 5 comes in the in-source line, that means 5 is telling me the answer. So I would check that 5 against here and say, oh, I better write that result in. Once I write that result in, I should clear this field because it's now good. I've got the answer from 5.
So the value of it is the person producing.
Yeah, so the in-source is, I'm going to tell you who's producing it. This is who I'm waiting for, the one who is producing it. So when this matches that, when write is asserted, that data value is the value to write into the register. We'll kind of draw that pictorially. But if you think of it conceptually, it kind of makes a little bit of sense. So we just need 2 pieces of data now. The actual data and who's going to make it. Good?
So you said when the redirection matches the in-source.
When the redirection matches the in-source.
That means the data's good.
That means that the in data is the data I want to store in the application. We'll draw that in, actual arrows in a second here. But hopefully it makes sense what we're talking on these. So far, so good? That's all we need. This is the only addition to your whole thing in order to allow this scheme to work. The rest of this is now producing those. That's why we only have here. Now I have one extra data type that's in here. Integer I. So what do you think an integer type is?
32 bits.
32 bits.
Yeah, it's an int, just like you're usually used to. Why do you think I might want an int?
Some sort of counter.
Because I'm lazy, right? And the rest of you should be lazy too. There's a smart lazy and a dumb lazy. What we want to do, I need to initialize this thing. There's a lot of data to initialize here, right?
Right.
So I really don't want to have to go through and initialize this by hand. Every one of them. I mean, I suppose I could. That's 32 times 2, 64 things I'd have to
We want
write
something
in.
other than zeros in there? You're trying to initialize
Well,
it?
even if I put zeros in there.
Well, doesn't just creating it initialize it?
No. Remember, you're in Verilog, right? If you don't assign a value to it, its default value is
X.
X. I don't know. So if you don't do anything else, you get a whole bunch of red X's inside your area. So that's not going to look pretty. So we got to be able to kind of set up some values in here. Now, this is why I made the int. So inside that initial thread that's in there, I just put a for loop. Now, like I said, Verilog looks like C. So this should look just like what you're used to. Right? For I equals 0, semicolon, I less the number of reg. That's a parameter that I have set up to be 32 is the number of registers. As long as it's less than 32, I equals I plus 1 is the only thing. You don't have plus plus. Sorry about it.
C, not C++.
A question
You can
about
see lets you do that though. So
Really?
Since an integer is just a 32-bit wire, can we access, say, the 5th bit of that wire?
So, technically, but it's a compressed number sheet. They don't want
so
you
I
to
can't
pull
go
bits
I
in and out.
brackets.
So it's really, integer is actually used just for this. It's used to implement something, so that I don't have to be redundant and boring. So in this case, it's not that I'm actually using this for an actual piece of hardware that's in there. In reality, when it goes to handle this, it would just unroll this for me. It's just a shorthand to allow me to write something that's going to be patterned one time. Yes. But that I could unroll that whole loop, and there I could have just written, you know, reg 0 gets 0, reg 2 gets 2, reg 1 gets 1, right? So it can technically unroll that, so it just writes all the things out for me. So the whole purpose of integer is to save me writing tedious code. I can look for a pattern and write it in there. But it doesn't actually, it's a one-time thing, so it just sets it up. It's not like it builds hardware up.
For initializing it, that's only for a test bench, though. Like if it was an actual FPGA, it would have at least something in there.
No,
Maybe
so
not zero.
it would have something, but it actually you don't know what it is. Right? So when I'm saying this, when I tell it to pull to 0 or whatever that goes on, I'm telling it clear the register. So at boot time, I'm telling it to assert an asynchronous clear.
And the initial will also run on an FPGA too. You put an initial
You
block.
can actually tell it to do that, and it will just load it in. And the reason why it can do that on an FPGA is FPGAs have a thing called a boundary scan. And a boundary scan allows you to redirect memory, any of the inputs from an external output area. You can access them from anywhere. So what we do is we store it. We have an external ROM on it, which is part of the boundary scan layer, and it just walks through and loads it into the FPGA. And your FPGA is actually a bunch of RAMs with transistors. Has everybody seen what an FPGA looks like?
Oh yeah.
I mean, it's not required for this course, but you know, it's kind of interesting. It's just a whole bunch of little wire interconnects that go in, that are going through. And at every possible area, I might connect this wire to this wire. So we just put a transistor, just
Just
like
a
we
bunch
did
of
for our
lookup tables,
DRAM.
right?
And we
Connected
have
to
a
each other
single
and you
flip-flop
fuse them differently.
that controls it. It's either connected or disconnected. And it goes through all possible connections. This thing right here could have a ton of different potential connections. It could go that way, it could go this way. Right? And so I have a gold D flip-flop. And I'll walk through each and every one of these. You know, put a D flip-flop and just all possible combos of 2 at every intersection joint. Has a bunch of D flip-flops. So now, where you connect the wires becomes load all the flip-flops. Right? And I can load those flip-flops on a boundary scan. I just walk around and just load all the data on them. So therefore, you know, if I want to clear a memory cell or something, I just write a 0 to it, but that's just writing to a flip-flop. So this initial would go into a boundary scan file for initial load into the system. All right, here is my suggestion. So this is pretty standard. I have to initialize reg file I and redirection I. So I'm just walking down through this table, right? 0, 1, doing both of them at the same time. Not redirected is a predefined parameter for 0, right? Just saying the data in it is good. When I first start up, all my data should be good. Why do you think I put I in there instead of 0 into the registers? Most people I know put 0 into the registers.
Well, that way.
I am a noted freak for
Because-
not putting 0 into there when I'm writing my code.
Now, if we ever have to change the value of I,
0 is hard to debug. Later on, when I go to implement, I'll change it to 0. But until I have fully debugged my system, I leave it at I. And the reason is, if you pull the wrong register and send it out, and every register contains the same exact value, you cannot tell if you just sent register 1 or register 2 out on that line. But if the value that goes out is identical to the number of the register, and I know I'm supposed to be sending
I
register
see.
1 out, and I see a 5 go out on the line,
Oh,
well, I
see.
know I just messed something up. It should have said 1 goes out on the line. So it just makes it really easy for me on timing diagrams. And it's been one of those things that has avoided a lot of troubles because it's really easy to typo. And so anything that helps you find typos right, will save you untold amounts of time. Logical errors are usually easier to find than syntax errors, right? Syntax errors beyond the first couple ones, things like that where you accidentally put the wrong number in there are extremely difficult to find. So I heartily recommend that initially you set this to I, and then when you are ready to finally release it, you reset that to become 0, which is what you really want clear. But up until then, it's more useful to have something debuggable about. So that's my suggestion here. There's only 2 things you have to do, which we've already mentioned. You have to handle issues and updates. So the issues are going to come in on the negative edge of the clock, and it's going to tell you, I did an issue, you'll see the issue flag come up, you'll get the A address, the B address, and the destination. You got to get the values of A and B, see if they're any good, and shove the correct values out on A data and B data, and set A invalid and B invalid according to whether the data was good or not. And then the destination, you have to set for whoever is going to be writing to it, you have to set up the redirection buffer to look for. It's a lot of stuff, thankfully. Thankfully, we can break it up into little pieces. Think of what happens in an issue. When an issue happens, what goes on? Somebody has to tell me it's an issue, right?
All right.
So I have an issue flag, which means the command or the flag issue has to be set to be 1. So I'll put double equal here just to say you're checking, is issue equal to 1? All right, so you realize I'm not saying assign issue to 1. Issue should be equal to 1 when this is happening. They're telling me it's an issue.
The issue flag's high, yeah.
Yes. All right. Now, at this point, I get 3 addresses, and I have to send 4 pieces of data out.
Right.
The 3 addresses I get are the A address, the B address, and destination. Do we all agree?
Yes.
Okay, that's given to me. What data do I have to output?
A and B data.
The A and B data, and that's 2.
Yes.
I need 4.
Do we have to put out destination? No.
And A invalid and B invalid. I have
Oh.
to set the booleans.
Well, yeah.
Okay, so 4 pieces of output data. Well, let me ask you a question. How do you know how to set A invalid or B invalid? Let's just say A invalid.
Based on the register file.
Not on the register
Not
file.
on the register
It's
file.
coming from.
Flag.
On redirection.
Right.
Okay, so how do I know?
Check the redirection.
Okay, check where in redirection?
Check bit I of redirection.
So I would have to be checking to see on this, right, if redirection is the name of this whole thing, which entry of redirection?
The I entry or the A invalid.
How do they tell me?
What?
Somebody has to tell me, right?
Not destination.
Destination is one of the sources.
No, it would be in source.
A address.
In source is somebody writing me an answer. So
Oh.
this is an answer.
No.
See what I'm saying? The most important thing is know what your variables mean.
Right.
I'm trying to find out whether A is valid or not. Who will know who A is?
A address.
RS calculating this.
A address.
A address, yeah.
If you want to know who's A, why don't you look up A's address?
Which makes sense because redirection's a 32-bit.
Ah, and it's a 5-bit number, right?
Right.
So the names are meant to actually help you. If you want to find out which one of these 32 is A, look up A's address. So redirection what?
Redirection of A address.
A address.
If that equals 0,
Huh?
data's good.
Yeah, so you can check to see if it's equal to 0. You could decide to check, is it greater than 0? I don't care which way you do it. If it's greater than 0, it's
Bad.
Bad.
invalid.
So we can just do if not redirection, right?
So, all you need to see is 0 or not 0. I don't care which way you check it. You can check if it's equal to 0, and then the else condition handles the bad, or you can check greater than 0, and the else condition handles the good. Your choice on how you want to check it. Let's assume, just for the sake of argument, I just do this one, right? I check to see if redirection is bigger than 0. What do I need to handle? If redirection is bigger than 0,
A invalid becomes true.
Then you get the follow redirection of
okay,
the
so A invalid has to be true.
Right.
A invalid is true. And I think I made a flag for true.
You did.
I'm not going to bother with semicolons. That's your job. I'm writing pseudocode. Right?
Supercode.
What else do I have to say? Or am I done?
No, you're not
Well, we
done.
know it's invalid, so we need to know where the data is coming from.
Right.
Okay, that's what I
So
have to say.
destination. No.
We need to look into that
A out needs to be that.
redirection address.
Yeah.
Yeah, is it, do we call it A out or A data?
Yeah.
Yeah.
And A out should be,
Redirection of A address.
You're doing blocking statements. Do they have to be blocking? Or
what's that?
We're worrying about that.
oh, gotcha.
Yeah.
Pseudocode. Gotcha.
Actually, I would suggest, but I told you, I'm not writing Verilog for you. You should handle the non-blocking stuff.
Well,
I'm
sometimes
writing pseudocode.
I was wondering because sometimes it matters.
It
does matter.
always matters, but I'm writing pseudocode, and pseudocode doesn't have to run. Right?
Yes.
Okay, so, but realize that, and this is something very important. When you first are coming up with something, if you screw around with syntax, you will never get the idea done.
That's true. Yeah.
Okay? You really will not. The most important thing, see, computer science and computer engineering are the same exact thing. Most people don't get this, but there really is not a difference in this. What you do in both cases is you come up with an algorithm to solve a problem.
Right. We
Right?
just use different
And then you
mediums.
implement that algorithm in some type of a predefined language. It could be a software language, it could be a hardware language, it could be an actual gate combinations, which itself is
Is
a
a
logical
language,
language. Right? So I don't care which way you want to go with this, right? Whether you want to go hardware, software, it's just an implementation of an algorithm. So no matter what you're doing, right, we put these arbitrary titles up there, and it just tells how much hardware experience do you have. That's really what it's telling you as it goes. Are you more a hardware person or a software person? But if you understand the idea behind it, you can do either one. Right? I'm a computer engineer, but I teach computer science courses. I have no problem with that.
Yeah.
Right? So, you know, and my point to you is just this, that, you know, if you understand one, you can do the other. A computer science person can teach a computer engineer course under those same ideas. I mean, it's, you understand the ideas, you can implement it. It's really one thing. So what I'm trying to do with pseudocode is to express the idea. Once you've expressed the idea of what needs to happen, put it in whatever language you want. Put it in Verilog, put it in VHDL, write it in C++, stick it in Python. I could care less. Right? Write it up as a bunch of gates. You can turn that into a bunch of logic gates. That's the whole point of 310, is how do you turn something like this into a bunch of logic gates? It really doesn't matter. Right? If you understand it's only one thing, you only have to remember one thing. Right? So, that's, I mean, we really have one trick, we just dress it up fancy. Yeah.
I like using the parameter valid for like stuff like if redirection is equal to valid. But like in this one, the parameter is 6-bit of 0. Does that matter if I'm comparing it to 32-bit of 0? Or
But redirection is how big?
32
it's
bits.
32 bits?
Please look again.
No, it's 6 bits.
Oh.
It is 6 bits. Yeah.
Sorry.
Okay.
Wait, I
It's
thought.
32 6-bit
Yes.
register.
Yeah, that's okay. That's right.
But the second I've done this, I've removed the 32. This tells me which of the 32, and that leaves me a particular one of the 6.
Okay,
It's
so
6 by 32, and this knocks it down to just 6.
What if I did something like that? Would it just compare the last 6 bits of the one that's bigger to the 6 bits of that one? Okay.
which may or may not be what you want.
Yeah.
You know, and probably would confuse the hell out of anybody else that's going through it.
Great watermark.
So, the fun thing is, as you're going through these, you could actually redefine all kinds of stuff with parameters to check them, so you can make it very English-like when you're going through. I wouldn't make it excessively too much. I'd make it at least to the point where it's readable by somebody, but just enough of the language left over that somebody who doesn't feel comfortable with it won't know what to do. At this point, have I handled everything I need?
No.
No.
What else needs to be done?
Let's see. So we have
Oh.
to do something with let's see. So we output. Let's see that. What are we doing? What about destination?
We've sent the value out. What else needs to be done for A?
I don't think anything else for A, but overall.
Okay.
So won't the redirect address to redirection of address A address? That's not really the focus value, doesn't it?
Redirection A address. We said redirection A address was not 0.
Yeah.
So redirection A address must be the reservation station that's producing it.
Yeah. Okay.
So that'll send whoever's producing the reservation station number who's producing it to A out.
Okay.
That's what I want, right?
Right.
Okay.
And the other bits above it will be
0.
Wait, say that again?
what will the bits above it be? This is only 6 bits. That's 32.
Want to get
Did I
the sign
put 0
extended?
there?
Did we define it as signed or unsigned?
Yeah, so you gotta look at how does it extend that number.
Gonna sign
It
extend.
only signed extends if you make it a signed number,
Oh really?
Yeah, 0 paths otherwise.
Oh okay.
right? But since I'm putting 6 bits into 32, okay, depending on, I've seen different ones do it different ways. It's supposed to actually just affect those 6. Okay? If you want to make sure, and this would be my strong suggestion, you know, under this circumstance, and you're never really sure where they do it, like Icarus Verilog does it one way, and, you know, which is proof of how it's bad. Okay. But, you know, I would actually suggest at this point, since this is only 6 bits, I would append the remaining missing 26 bits. So I would just use the append command, curly braces, and I would put 26 bits of binary 0, and then now I got a 32. Now I'm guaranteed I get the zeros. Whoa. Okay. But it's technically not wrong. The other side should only listen to those 6 bits anyway, so who cares? Now, technically, in a bigger system, if I don't set these zeros, it's not as pretty, but what does it do?
If you don't.
It does actually do something. If I don't set the 0, and I just let them float,
Well, then they would be X's still, right?
they'd be X's still, which means I'm not asserting power on those lines.
Oh, so
Less power, less heat. So if you're interested in building a power saving system, which a lot of systems are, you actually let it float. And don't assert the wires.
So
Save the power transmission, which means you save the heat buildup on the chip. So you save a lot of stuff when you do that.
so even if we assert zeros, we still assert heat. Like we
Of
still.
course I do, because I have to drive it low.
you gotta pull those, you gotta sink power.
I have to ground it. It costs power to remove the charge that's in there. Right? It seems funny to people that grounding something costs power, but you know, just remember, anytime you do anything, you know, you're contributing to the heat death of the universe. So,
Yeah.
okay. All right, so this is what happens if A is invalid. The else condition will happen when
It is valid.
it's valid. You ought to be able to figure out the rest of it. All right?
What do we
Yes.
do with
Oh, A out will actually be our register at the address.
So you ought to be able to handle this pretty directly, right? On the first lab, or lab 2 that we went through, I coded the whole thing. in pseudocode and you just had to do it. Here I'm only going to go halfway. You ought to be able to figure out how to take and convert this one for the other.
Okay.
How about for B?
Same thing.
Same thing, change the letters.
Right.
Okay, so now I'm down to 25% coding. Right?
Copy and paste.
Dot.
Control C, Control V. Done.
So the only thing you have left now is what?
We have to.
We just took care of the
You've taken care of all my outputs, right?
Right.
right.
So what do we do with
We're
destination?
still handling issues then?
We're still doing issues.
Yeah.
We've got issues. We've got a lot of issues.
We still have to set the
So-
destination, right?
Yes, we still have to deal with our destination. So what do we have to do with destination?
Well, we have to set it for whoever's writing to it, so... Oh, wait. The in-source is the one that's writing right now, right?
In-source is who's writing the answer. Is somebody writing my answer yet?
Destination is who's requesting it, correct?
Destination is the particular register that's going to be written to. But it's not ready to be written to yet. It's just telling you, because of this command that's coming in, that destination is going to change. So destination is the register that's going to change. Who's going to change it? Don't I need to know that?
In-source is going to be the
In-source is not the one who is going to change it.
RS calculator.
Remember, in-data, in-source, and write are your common data bus. That's writing the actual answer. Okay? So this is only at update time. So these three are update. Otherwise, ignore them. Update only. By process of elimination. Okay? Why?
Process of elimination.
But look at the name.
Yeah.
What is RS? Reservation station.
Calculating.
Reservation station that's doing what?
Calculating.
It's calculating the value. So when I'm looking for who's going to calculate the value, maybe I should find out which reservation station is calculating the value. Okay? So my comment to you, if you name things well, it should actually remove the need to process of eliminate. If you don't name things well, then you really better rely on a good interface spec. It's best if you have both. So in our case, reservation station that's calculating the value is the one that's going to be changing things. That's the one that will produce the result for the destination. So how do I tell this thing? Let's say the destination was 4. And RS calculating was 2. What would I do?
Change RS calculator.
Right? So we just know, the RS calculating is just outside variables, right? RS calc, what did I say it was? RS calculating was 2, and dest was equal to 4. What should I do in this file? Let's just call this 0, 1, blah, blah, blah. What do I do?
Oh, so calculating 2 means it's the second reservation station that's calculating? And so do we reroute the calculating to the destination?
I'm asking you.
Oh. Well, I'm throwing a curveball and asking you.
Yes, I know. You're answering a question with a question. Good job, Socrates. That would have worked maybe about 3,000 years ago, or 2,500 years ago. But unfortunately, I'm a professor and I don't feel like working. Think about what it means, right? What did each one of these errors go? Range file holds what?
Or
Holds the data.
data, right.
What does redirection hold?
The address of who's got your data.
Yeah, where the data should be coming from.
So it's holding the reservation station number of who is producing your data.
So it's holding R as calculating.
Okay. Who should be holding RS calculator?
Redirection.
Yeah, in redirection, so I've got to find the correct one, right? There's 32 of them. Which one do I put it in?
The destination one.
Destination. So I go 0, 1, 2, 3, 4, and RS calculating is 2.
Oh, I see what you're doing here. So, redirection.
So I'm telling register 4, that's why I counted down to spot 4. It starts at 0 and goes down. So I have to tell it in the redirection area, not in the reg file. Right? Reg file holds data, redirection holds reservation station numbers.
Uh-huh.
So in the redirection area, because I'm going to write a reservation station number, in redirection of destination, I write the value of RS calculate. How do I say that? Pseudocode.
Redirection of destination equals RS calculating in source. I don't know if you're shaking his head or nodding. Right.
Alright, that just tells you, go to redirection, go to the destination line, because that's the particular register value inside there that we're talking about. Go to its redirection area and stick who's going to produce it in that spot, so it knows who's going to produce it. From then on, anybody asks for it, when it comes in, they'll see 2 and they'll go, oh, go to reservation station number 2. That's the one who's producing it. Until it actually produces its answer and it overwrites the correct value and blows away who's producing it. Does that make sense? So that's the easiest one to handle. But notice, you cannot just guess. You must know what it means. This is why it's so important to understand. If you just copy the code I write down here, you will get something that works, and you will never be able to produce anything again. Okay? So, code is non-helpful. I know this is hard to believe because everybody's used to, oh shit, I've got an assignment due, I better go to Google and find Google code, and somebody will have written something that looks pretty similar that generates something reasonable and I can tweak it.
Who does that?
Okay? You know. Color me surprised. Okay? But the reality is, that's great in the end when you know what the heck you're doing. And I don't deny that people in industry do that. Of course they do. But by that point, you ought to know what you're doing already. This is the time to figure out what you're doing so you pick the right code and stick it in. Or you pick something close and modify it to make it reasonable. But if you don't know what you're doing, you're doomed. Looks reasonable, stick it in, who knows whether it works or not. And you have no ability to debug that. So the more you spend on trying to subvert the process now, the worse it will make your debug time and the rest of your career. The more you spend the time now to understand what's going on, you'll never do this again, right? You know, you might, if you're a hardware person, do a variant of this, but you will have to figure out how that's going to work, because this is out of order execution if you deal with any modern system, and you're going to have to deal with how to turn a description into functioning code. We give you pictures and descriptions all the time. You have to figure out the algorithm. You have to figure out how to code the algorithm. This is very common. And believe it or not, for most things of value, Google code doesn't have it. If all you ever do is generate generic crud, which will bore you off your rear end, then yeah, you can find Google code for it. But if you're doing anything worthwhile and fun, it won't be there. Okay? They can only give you little snippety codes that might give you an idea what it might look like. And then you have to figure out, oh, that's how I code in this particular language, and you can pick up language ideas from there. But I'm not going to actually help you with your real work.
So now, do we only have to do this if A or B are invalid?
So only if A and B are invalid do I have to fix the destination.
Right, because
Remember I said you had to do A,
right,
and then you'd have to do what you did for A for B.
right.
But you always have a destination, don't you?
Oh, gotcha.
Right? Now, there are times when you don't have a destination. branching instructions, storing, things like that. But do we have branch instructions?
Not yet.
No. Do we have stores?
No.
No. So you don't have to worry about it. You don't have an AOU, so this is all you have to deal with. You would change this. This is where you would put something in to see if it has a destination. So it would have to be part of a class of instructions that's modifying the register file. And so that would be a signal that would have to come from your control unit. That would tell you, and then you would, assign the destination based on that. But every one of our one does, so I didn't see a reason to put a flag in for it. Make sense? So if you understand what we coded there, you can actually write up that whole part of it. Now, what I would like to then do, if you understand that, and you were successfully able to do the previous one, you know how to handle updates. I'm just going to give a brief rundown. In an update, right was set high. So what should I have to do? You have to check to see if right's high. Then you see if your redirection buffer has this source. So how do I find out if any particular value in my redirection buffer happens to have in source?
Somebody will loop through it.
Redirection.
I have to check them all, don't I?
Yeah.
Okay, so you can do it the slow way and write it all out, or you can use my integer I, and you can probably write a for loop for that, couldn't you?
Let's just get flattened out anyways.
It'll get flattened out at implementation time. There's actually a really nice command to do instantiations automatically inside of loop 2. It's called a generate command.
I was going to
So if
ask
you're a
you-
hardware person, there's this command called generate, and it allows you to stick instantiations inside of for loop.
Does it allow you to do for loops outside of threads? Because that's what I used it for.
So there's special syntax for generate to handle this, but it basically allows you to generate a bunch by pattern. So you check to see if we're writing. You check all the way through the redirection buffer for the in-source. There could be multiple, theoretically. Right? Not likely, it should just be one, but you could check. It could, and under some weird circumstances, maybe have that. And then, if it matches, what happens with in data?
In data goes to the destination.
Right? If in source matches say in source was 2, I look through here and I go, ooh, I found a 2.
Right. That gets
In
replaced
data.
Where does in data go?
to the
of a
destination
register.
of the register.
It goes here.
Yeah.
Don't talk destination anymore.
The redirection.
Destination is gone. I know it's here, therefore it's the same spot in reg file that I am inside here. So if I'm walking through this on I,
Reg file.
and I discovered that redirection I happens to be equal to in source, then it's got to be reg file I must be equal to in data.
Right.
Right? And what should happen to this?
0.
0.
There you
So
go.
reg file I equals 0.
Presuming that you actually did find it inside in source.
Yes. So I'm going to do one.
So you have to check, you have an if statement. And
Yeah.
so I gave you a brief rundown in verbal description.
Wait,
You ought to be able to generate the pseudocode for that.
That's all you have to do for that one?
I
Wow.
told you this was very easy. But if you look at the thing, I don't give a lot of time for this one. Because it's really two very simple loops.
See you next Monday.
I believe I only give you a week.
Okay.
But I'm not, I'm just a professor.
I signed it.
It's above my pay grade.
Yeah, see you next Wednesday.
Next Wednesday?
Yeah, on the 6th.
That's like a long time.
It's a week and a half.
Yeah, that's a long time. That's how much he gives us for all the labs.
So, but this one, it's not too bad actually. Right? And I already give you, so in addition to this, I give you a full test bench that goes onto it, right? Registers test as it goes in. So I've got them all set up to with all your necessary signals to test this individual one that goes on. All right, so you have a test bench again here. I encourage you to look through and see how I produce these, because I won't give you them forever. Okay, and then I instantiate registers. Again, as it goes. Notice I don't instantiate adders and registers. This is a unit test. I test registers by itself. You're going to have to integration test it. So I have much fun.
So we're going to have to write another test bench to include the...
Eventually get there. You don't have to do it at this instance. At this instant, I only require you to do this. You know, if you want to, you can do that, in which case it will probably save you some hassle later on. There's only one more thing we have to program, and our system will be ready to go.
Scoreboard? What do we do after that? Because I mean, that shouldn't take too much longer.
Yeah, that one's a lot more.
Okay.
That one, if you notice, I put a few weeks on there.
Oh,
So
all right.
that one has a bunch of stuff that goes on because it has to track everything. Everything anything does, it's got to track and update. And then it's got to reshuffle because it's a queue. So we have to reshuffle and clear memory. You got to make sure you don't clear memory at the wrong time or you get data collisions. There's a lot of little fun issues on data manipulation that come up with that one.
Are we writing that one from scratch? Or are you giving us a starter point?
I actually do give you a starter point. I can.
Oh, you're too kind.
I am exceedingly kind. See, for that one, see, I give you the interface and a whole bunch of parameters.
You tell us. Oh, and even initialize it for
I
us.
actually initialize the stuff for you,
That's all we gotta do.
and I give you room to decide what threads you're going to have to do.
Oh, we
Because by
just
that
save
point,
it
you gotta know
in
what
test bench
threads
right
you
there.
need to do. Okay, so I give you plenty to start.
You let us use imagination. What more can we ask
Don't
for?
worry, you can keep adding. I allow your imagination free rein. But I do actually give you the data, the correct amount of data. I do give you this, but you are going to have to figure out the threads
So-
and what part of the clock pulse to listen.
Is it a safe assumption that we should use every single one of the parameters you gave us?
Oh, yeah.
I did not waste anything. But there are different ways to do it. There are options, and we'll talk about when we get there.
Okay.
But I would not suggest getting into that one on there. But the point is, right, as we're going through this, I'm giving you less and less data. Right? In the beginning, I got to give you a bunch because I got to get you warmed up. As we get towards the end, you have to be able to produce stuff.
At least you gave us a test bench. That's nice.
And then we're going to actually, after that, there's one time for an integration testing. So I do have a thing for integration test to set the computer up. Because once you do that, there'll be a couple more things. You have to get something that handles a bus master. And our bus master and a clock generator will be real easy to produce. But I don't make those separate modules because they're small potatoes. We'll add that at the integration time. So that'll be the lab after that. And then the last lab, you will take this and we'll write a program that has to run on it to calculate. I think it's the pentagonal numbers.
Awesome.
So what are we missing for this one?
For the one that you have here,
Yeah.
if you understood what I walked you through, you should it should be, you should have to turn this into actual Verilog.
so-
And
so-
you should turn my rough talking into an algorithm and then into Verilog.
So after we write that for loop in the second thread, we're done, right?
Yeah.
Oh, because I think you said we needed one more, and I'm sitting here looking. I don't see what else I need.
No, I said there's one more module when this is all done.
The out of order execution machine.
The,
Oh, okay.
the one that actually issues commands.
Oh, gotcha. Okay. How hard can that be?
There's only 3 little components to our area, so we're working on the second one here.
Gotcha.
Like it's all.
So the adders are easy, relatively speaking, to understand, but there's a lot of stuff to it. The reg file is pretty simple, but it's a good transition to you taking over. The last one's a decent amount of work and is a good sorter out, bringing you to the land of being mature as a Verilog programmer. Any questions?
Kind of an off-topic question, or your okay.
This is the one where we have I put case statements in it, and we're supposed to put that delay. Do you want each one when we do an ad to have its own delay? Or do you think that now? I mean,
Yeah, there's a lot of ways to do it.
it's not too. Yeah.
There's several spots you can do it. If it were me, I would do it as a single command later. And the reason why is it's one command as opposed to a whole bunch. You know, which means later on you would be replacing this thing by real hardware. And you don't want to have to go back and replace a whole bunch of little things. It's just easier to stick one. All we want to do is produce the answer and make it wait long enough so it